Well, yeah, welcome. It's really gratifying to see the number of people here who are interested in using GENI for their research. Looks like we have a good mix-up. We have some people from campus IT, regional networks that will be deploying GENI resources. So it's good to see the mix. And as I said earlier, please do feel free to stop me anytime if you have any questions or want to make comments. I will reserve the last half hour to do the demo. You can ask questions then too. I just might rush through some slides towards the end if I need to get to the demo. So kind of the outline for the talk. We'll talk about GENI and how it can be used for network research. Describe the GENI concept. Say a little bit about how we are building GENI. Talk about GENI experimenters, the kinds of experiments people are doing today with GENI. I'll talk about, just say a little bit about US Ignite. I see somebody from US Ignite here. And then future plans for GENI, and finally, what GENI looks like to an experimenter. So we already have global networks today that we use every day. The internet is, I guess, the best known global network. We deploy these networks, but we really don't understand the science behind these networks. We don't have the science to predict how a network would behave till we actually deploy it and try it. So most of our deployments are based on engineering judgment and learning from how they work. The NSF would like to actually build a science around this network so we can predict how these networks are going to behave, and we can use scientific methods to deploy these networks. We have innovation issues with today's network. So we use the internet. It's a production network. It's used for all kinds of mission critical things, such as sending Facebook updates and banking and the like. So really, since it's a production network, you can't go and tinker with the core protocols of the network. You cannot go to AT&T and say, hey, I have this great idea for a really cool routing protocol that you should deploy. They aren't going to let you do that. So all the innovation that we see happen today on the internet happens at the edges. You have new kinds of services being deployed. You have new kinds of clients being deployed. But there is almost no innovation in the core of the network. If you go to a networking conference, you see all these papers about new innovative routing protocols, but they don't go anywhere because you can't deploy them. And finally, there are societal issues. We use these networks, but we're never sure about about their reliability, about security and privacy. So to address all these science issues, the National Science Foundation has multiple research programs to create these new protocols, but they also wanted a test bed that people could use to try out these ideas. So that's where GENI comes in. GENI is a test bed, an infrastructure for experimentation in networking, distributed systems, security, and novel applications. So and the important thing about GENI is it's an at-scale infrastructure, meaning you can run extremely large experiments with using large numbers of resources, geographically distributed, so you can get a real feel for how these ideas you have will work at scale. So GENI opens up opportunities for leading edge research. I see a lot of students, a lot of you here are just starting out on your research programs. Hopefully GENI will help you with your research. And also for rapid innovation, since you can program GENI at the core, at the edges, perhaps we'll have innovation not just at the edges of the network, but also in the core. There are two key concepts that underlie GENI. The first is the concept of a slice. You'll be hearing the word slice a lot, not just here, but also throughout the conference. And it's a key concept of GENI. Slicing essentially, GENI is a shared test bed. There are multiple experiments going on. There are multiple completely different kinds of experiments using different kinds of protocols. Slicing is the backbone. So you can program at layer 2, you can program at layer 3, so you can put your own network protocols, your own transport protocols. You're not limited to the TCP IP suite. So essentially, it opens up the network for a variety of different kinds of experimentation, and you can do this at scale. Here's a little graphic that explains the concept of slicing and deep programmability. So the graphic here shows the GENI infrastructure. There are end hosts. There are the network links. There are switches and routers in the network. Here we have 2 researchers running experiments. Each experiment runs within a slice. So a slice is the isolation mechanism between experiments. And within a slice live the resources used by the experiment. So in this case, this experimenter here might have a virtual machine at this host, perhaps virtual machines on other hosts. So virtual machines being the slicing mechanism for hosts. This researcher might have a certain number of certain VLANs, Ethernet VLANs in the assigned to her slice. So that's the isolation mechanism within the at layer 2. And she may also have there's a technology called OpenFlow that allows you to slice your routers and switches. So she may have certain ports assigned to her experiment, certain flows assigned to her slice that she uses for her experiment. And likewise, the other researcher there, he might have similarly in his slice, virtual machines, slices of the network, VLANs, slices of switches and routers. So now we have 2 people doing experimentation on the GENI infrastructure at the same time and isolated from one another. Any questions so far? And they can both put their own software anywhere in the network. They can install their software on the end host, on the intermediate switches and routers. Okay?
So the GENI is only OpenFlow?
No, that is a slicing mechanism. There are others. I'll talk a little bit about the Proto-GENI backbone nodes, which are not OpenFlow, but still allow you to put your own software there. But OpenFlow is I guess, the dominant mechanism. All right. So I have a kind of a cartoonish example to show how GENI might work. So here we have our researcher who, I don't know why he has test tubes, but he's a network researcher. So he has he says, well, the original internet was designed for linking computers. I mean, that's what it was for linking up supercomputer centers. And he said, we need a fundamentally new architecture for GENI, something that allows you to connect people. It's not about connecting computers anymore. So he comes up with this idea, he writes it up, and you have he sends it for review, and the reviewers, they say, well, how do you know it's going to scale? How do you know it's going to work? How do you know it's going to be secure? Well, so to figure that out, he implements his ideas in software, tries it out in his lab.Maybe he has a dozen or so machines. He tries it out. Looks pretty good. So he decides, well, I really need to try this at scale to show my critics wrong. So he goes to GENI. He says, well, I need a few wireless resources, WiMAX resources, so I can have real users use my protocols, connect to my experiment. I need some cloud resources for computing. I need some backbone networks with switches and routers. So he essentially creates a GENI slice, gets these resources, adds them to his slice. It's probably a fairly modest slice at this time, and tries out his software. And word gets around about this new cool service he has. People start using his service. They may not even know that it's a service running on GENI. All they know is, hey, here's this cool service that I can connect to from my computer or my smartphone. They try it. As more people start using his experimental service, he gets more resources from GENI, perhaps more network resources, more compute resources, more base stations. And he learns a lot. He publishes papers based on real experience with real users. And kind of this is how his users get to him. Some might come from their smartphones, through the internet. Some might have special applications installed on their computer that perhaps don't talk TCP/IP anymore. They just talk direct. It's his custom protocol running on their laptops that talk through can talk to a slice over a layer 2 network. So some might be coming. So some might use his service through using traditional TCP/IP through a gateway, and some may directly use his new protocol. And well, his experiment is a great success. So he takes it off GENI, spins it into a commercial service, makes lots of money, publishes lots of papers, lives happily ever after. And not to say that all GENI experiments are going to end up this way, but at the very least, maybe you'll get a PhD out of it. And so if you have a great idea for a new networking protocol, the place to go for funding is the NSF SAIS office. They have a number of research programs that fund basic research in networking. Once you are ready to try out your ideas on a test bed, we'd love to have you use GENI. The resources are available for free. You can deploy your experiment using large number of resources. You can deploy them across the country, and if your experiment requires it, you can even support real users. In fact, there are people doing experiments today running Facebook applications on GENI. So their users don't even know that they're using an experimental service running on GENI. To them, it looks like a Facebook application. And this is Dr. Felix Wu from UC Davis who's doing this. So, any questions so far? All right. So just to recap, so GENI is meant to enable at-scale experiments. By at-scale, I mean it's sufficiently large scale that you can convince yourself, convince review committees that it will work at scale. It's meant you can run both repeatable and in the wild experiments, meaning you can do your traditional design of experiment kind of thing, identify your controlled and uncontrolled variables, control your environment so you can tweak the various parameters, see how they respond. Or in the wild, which a lot of computer scientist experiments are, you just deploy it. You get best. You're trying to control the environment. There might be failures, there might be bandwidth, there might be congestion, but that's real life, and you just let your experiment run in that kind of environment. So the point being that you can either have tightly controlled environments, or you can let the experiment run and see what happens. And it's good for large scale experimentation. So how do we build GENI? So obviously we cannot replicate the internet. I mean, it's just too large. It would be hugely expensive. So the way GENI works is by taking advantage of existing infrastructure, existing research test beds, existing networks deployed on campuses, and GENI enabling them. What that means is we put a API on these resources, existing test beds, such as you might have heard of Planet Lab out of Princeton, you might have heard of EmuLab from Utah, you might have heard of the Orbit wireless test bed out of Rutgers. So there are a variety of these test beds that have been built over the years. What we do in GENI is put an API, an interface onto these onto these test beds, and also networks, backbone networks such as Internet 2 and National Lambda Rail, campus networks which are OpenFlow enabled, which essentially allows you to use the same network for production and research. And so now as an experimenter, you have access to, access to all these different test beds and networks using a common API. So the tools you use, the experimental tools you use, can now talk to these diverse resources in the same way. Your one GENI account will give you access to all these different resources, existing test beds, campus networks, WiMAX base stations, and so on. So that's how we get to scale at GENI. It's by GENI enabling a heterogeneous infrastructure. So this our researcher here, when he creates a slice and adds resources to the slice, the resources might actually be coming from different organizations, different universities, different network operators. But he doesn't have to know that these are different. To him, they're all resources with the same kind of API to access them, to discover them, to get them, assign them to his slice. And he needs just one account. He doesn't have to get separate accounts from all these different test beds. Okay? We'll see an example, and hopefully it'll be clearer as we go along. Oops. And one of the areas where there's a lot of effort in growing GENI is on campuses. So GENI enabling campuses is a key piece of GENI's growth strategy. GENI enabling a campus means one of two things, or both. It could be installing what's called a GENI rack, which is essentially some compute and open flow switches in a campus, on a campus. The other is open flow enabling the campus. What that means is open flow is a technology, as I said, that allows you to partition your network so you can use it both for production and for research without the two interfering. So, and a lot of the commercial switch vendors have essentially firmware upgrades you can do to this switch to open flow and enable them. So now, when you open flow enable a campus, now your campus network can be used for both production and research. Students on campus can now access novel services on GENI using new protocols that experimenters might be deploying. And students are typically are early adopters of new technology. They're more willing to try novel services. So getting to campuses is a key piece of the GENI growth strategy. Georgia Tech, for example, is one of the early campuses where GENI was deployed. Key to success for a campus deployment is researchers on the campus working with campus IT, which is why it's really great to see this large presence from University of Wisconsin, for example. We have campus IT, we have researchers, and that's key to success. Yeah, the researchers have the campus IT folks have to trust the researchers when they say that yes, this technology is good and it's not going to hurt your network, and campus IT and they cannot do their research without campus IT's help. This is kind of how all this works. Essentially, we still continue to use the internet, so the TCP/IP stack suite of protocols running on the internet for GENI's control network. The control network is what is used to discover resources, to set up resources in your slice. So you use the internet to go to different test beds or campuses and say, I would like a few computers from here, I would like a VLAN from here. So essentially that protocol happens over the internet. And you use the control network to essentially stitch together your network topology. And that doesn't have to be TCP/IP. That is on a completely different research network. The backbones might be Internet 2 or National Lambda Rail. There may be regional networks involved that give you VLANs through their network. So you're using the internet to stitch together your experimental network. On your experimental network, research backbone side, National Lambda Rail and Internet 2, it's the piece that's missing. Is the reason I've told you how we are building GENI essentially by GENI enabling existing resources. Now I'm going to tell you about how people are using GENI. So in their application, they had weather radar information coming from their weather radars going to a cloud computing site. They were using Amazon, I think, for their computing, and then using GENI backbone networks to be able to not only carry these large amounts of data, but get the forecast to wherever it was needed. And they would essentially set up the topology, the custom topology the experiment needed using GENI. So they needed Amazon resources connected by a layer 2 network to their encouraging both private enterprise and experimenter. So if something goes wrong, we know who to go after. So if your experiment does something bad, I want a node, I want to call it my node, and exclusive so only I can use it, and I want a raw PC. So all this for just getting one computer. And again, as I said, fortunately you don't have to. And we'll save that. So I got a server.